Welcome back. In the last part of this lecture, we're going to be looking at two more functions less nice than the first ones. So we've seen a polynomial, we've seen a couple of rational functions, but I wanted to do some that weren't things that we could just do with pre-calculus skills. And so this is a good example of a function where pre-calculus will not give us enough information to graph. We have a function that's not a rational function anymore. It's not a polynomial in the denominator. So we don't have clever little rules to figure out how our asymptotes will work and all the rest. So first off, let's think about domain for this. For sure, I've got a denominator, and there's two things I have to worry about. I have to worry about, is the denominator ever zero? I have to worry about, is the inside of this square root ever zero? Is the inside of this square root ever negative? So the one thing I might notice, of course, is x squared plus 1 for sure would never be equal to 0, because you would need x squared to be equal to -1. So you know that you're never going to have the denominator being 0. So we know that that's a good thing for us. The second part that we know is, if we're thinking about the function itself inside that square root, could it ever be anything negative? So in other words, if we're wondering, is x squared plus 1 ever less than 0, do we ever wind up with something not being a real number here? That would only happen if x squared were ever less than -1, and that also never happens. So in other words, the inside of my square root, for sure, the smallest it'll ever be is 1, which means that the square root will always be defined as a real number, and it also means my denominator will never be 0. So actually, I've drawn a few conclusions out of this. The denominator is never 0, which means we're not going to have any sort of asymptotes. And the inside of my square root is never negative, which means this denominator is never going to be undefined as a real number. So my domain should be all real numbers. So I don't have to worry about any asymptotes now, vertical ones at least. If my domain is all things, then there are no vertical asymptotes and there are no holes. If we're thinking about intercepts, I can spot those really easily. I have, for the numerator, it's equal to 0 when x is -3. And my function, when x is equal to 0, the y value would be 3 over square root of 1, which is just 3. So x-intercept and y-intercept, easy enough for us to find. Let's start with the calculus side of things. So asymptotes. If we were looking at x going to infinity of x plus 3 over square root of x squared plus 1. So I have some of my things are inside of a square root and some are not. I know that if x is bigger than 0, I know that x squared, when we square root it, it's the same thing as x. And that's because if I'm putting a positive number in, then the squaring and square rooting won't change it. I'll get exactly that same number out. So that means if I wanted to divide the top by x, then I can divide the bottom by square root of x squared. And that's fine because x is going to positive infinity. So we are talking about positive values of x. So that means we would have limit x goes to infinity of x divided by x would be 1. 3 divided by x would be 3 over x. And then inside the square root, when I divide x squared by x squared, I get 1. And when I divide 1 by x squared, I get 1 over x squared. And now I can see that for the top, it's going to 1 plus 0 over the denominator, which is going to root of 1 plus 0, or in other words, 1 over 1, which is 1. And if I do the same sort of thing on the left side, if I say, well, what happens if we're approaching x, x is approaching negative infinity, for that one, on the left side, I'd remind myself that if x is less than 0, then if you had x and you squared it, then square rooted it, you have changed the sign. So in other words, the square root of x squared is the opposite of whatever x is. If x was -1 and you squared it and then square rooted it, you would get the opposite of -1. You would get +1 instead. So in other words, if I'm dividing things inside the square root by x squared, then on the top I'll be dividing things by -x. So my x plus 3 over root of x squared plus 1 will become a limit. X goes to negative infinity of dividing the top by negative x. I'd have a negative x over x, which is negative 1, 3 over negative x, and inside the square root, I'll divide everybody by x squared. X squared divided by x squared is 1. 1 divided by x squared is 1 over x squared. And I have that on the top, it'll go to negative 1, and on the bottom, it'll go to root of 1. So we'll get negative 1. So this function is going to have two different horizontal asymptotes. It's going to have a horizontal asymptote of y equals 1 on the right side of things, and it'll have a horizontal asymptote of negative 1 on the left side of things. So I'm going to quickly jot that down before I forget. So on the right side of things, we're going to have a horizontal asymptote of y equals 1. And on the left side of things, we were going to have a horizontal asymptote of y equals negative 1. Okay, and the other thing that I wanted to make a note of were my two intercepts. So I had my x-intercept at negative 3, and I had my y-intercept at positive 3. There we go. And so now we're ready to start thinking about first derivatives and all the rest. So we have our function. We know it's defined everywhere. We know that our denominator is never going to be 0, which is nice. So let's find out what our first derivative is. And so when I look at my first derivative and clean it up, we will find that I named the function y, so I'll call my first derivative y prime. The first derivative cleans up to give me 1 minus 3x over x squared plus 1 to the 3 halves after I do quite a bit of cleaning up. So for this, I know, again, the denominator is never going to be 0. We already gave several moments of thought to that x squared plus 1 could never be 0. In fact, it could never be anything negative, so I'm always fine to square root it and cube it afterwards. I have y prime is never undefined. And I do have one place where the y prime could be equal to 0. And that's when 1 minus 3x is equal to 0. Or in other words, when x is equal to 1/3. And if we wanted to go back, you could find out that when x is equal to 1/3, y would be, if we put that back into the original function, you'd have 10/3 on the top over root of 10/9, which after a little bit of cleaning up would give you y is square root of 10. So we have one point, which is this 1/3 root 10. Root 10, that's about 3.162-ish. So when I plot that point, it'll be a little bit above 3. I have just that one critical number, so I only have one place where my increasing versus decreasing could change. And so if I were to look at my first derivative at 0, it turns out to just be at 1 on the top and 1 on the bottom. So 1, first derivative is just 1, which is positive, so we're increasing. And then after 1/3, I could go for 1 as an x value, so y prime of 1. That'll give me a negative 2 on the top and 2 to the 3 halves on the bottom. And again, I don't really care about the actual number itself, only the fact that this is something negative, which tells me that we're decreasing. So 1/3, it's a point on our graph. It's a point where we have a derivative of 0. We increase before it and decrease after it. So that means that we have a maximum at 1/3 square root of 10. So I guess I'm going to start plotting that on my graph. So 1/3 square root of 10 is going to be a max. So Square root of 10 is like 3.1, so just a little bit above my y-intercept. And I'll just label that for now. So I'm going to for sure have a little max moment. It's of course going to connect to that y-intercept and then curve downwards after that. So I have to figure out, though, concavity, how that's all going to work. So for sure, I'm going to make my way to this x-intercept and then become horizontal. I don't know how my concavity is going to change, how many times even it's going to change. Same thing on this side. I mean, I'm going to eventually make my way down to this horizontal asymptote, but again, there's going to be concavity issues to sort out. So now next part. Now that we've dealt with our first derivative, 1 minus 3x over x squared plus 1 to the 3 halves, then now we need to move on to our second derivative. And so for that one, when we find our second derivative, it cleans up to give us 6x squared minus 3x minus 3. And so for that one, if we're looking at it, and then of course over x squared plus 1 to the 5 halves this time in the denominator. Same thing as before, the denominator is never going to be 0 or undefined. X squared plus 1 is always positive, so taking a square root and then raising to the power of 5 is always okay. So the only place where we could have changes on concavity would be where the top is equal to 0. So first off, y double prime is never undefined. So now let's figure out where is it's equal to 0. So it'll be equal to 0 when we have the top equal to 0. For this, I mean, don't waste your time trying to factor this by hand unless you're really fast at factoring. Instead, just use the quadratic formula, negative b plus minus root of b squared minus 4ac. 4 times 6 times 3 is 72 over 2a. So I've got 3 plus or minus root of 81 over 12. And when you clean that up, that's 3 plus 9 over 12 or 3 minus 9 over 12. You'll get two different values for this. For this, I got one value. The 3 minus 9 over 12 is negative 6/12 or negative a half. And then the other one is x equals 3 plus 9 over 12 or 12 over 12, which is x equals 1. If we go back and figure out with our original function what the y value is, if x is equal to 1, the y value turns out to be 2 root 2. And if you put in an x value of negative a half, the y value is around square root of 5. Well, it's not around square root of 5, it's exactly square root of 5. What it's around is about 2.23-ish, somewhere around there. And 2 root 2, that's somewhere about 2.8, thereabouts. So I have two places where I might have a change in concavity. So now it's time for me to get my number line going. I only have two critical, or I shouldn't call them critical numbers. I only have two places where my concavity could change, negative 1/2 and 1. And if I were to look at value less than negative 1, like negative a half, like negative 1 rather, and then put that into my second derivative, it turns out to give me something that's positive on the top and positive on the bottom. So we're going to wind up with something that's positive. We are concave up in that interval. If I'm looking between negative a half and 1, easy choice to choose would be 0 for that one. And for that one, I would have negative 3 on the top and 1 on the bottom. I would have a negative value for my second derivative, so we'd be concave down. And then for larger than 1, if I picked x being 2 and I put 2 in, 2 would make the top positive and 2 makes the bottom positive as well. So my second derivative at 2 should be positive, which means we are concave up. So in other words, both of these points that we just found are both points of inflection. So we have a point of inflection at 1 to root 2, and we have another point of inflection at negative 1/2 and root 5. Okay, so let me just put those on my graph. 1, 2 root 2. And 2 root 2 was around almost 2.8 thereabouts. So there we go. So 1, 2 root 2. And then the other one was at negative 1 root 5. And root 5 was about 2.2-ish. So let's say thereabout. Oh, it was negative 1/2 rather. Negative 1/2 and root 5. Okay, so now I'm going to put together everything that we had. So for the beginning of our graph, if we're thinking about the increasing versus decreasing, we were going to increase until we got to our max and then decrease afterwards. So I will increase until I get to my maximum and decrease afterwards. As far as the concavity goes, I'm increasing until I get to my maximum, but as I'm increasing, I start off being concave up until I get to my point of inflection. Then I'll be concave down and increasing until I get to my maximum. I'll continue being concave down till I get to my next point of inflection. Now I'm decreasing. I'll continue decreasing, but I'll be concave up towards the end. And on the right, I'm getting close to that horizontal asymptote y=0, and on the y=1, and on the left, I'm getting close to that horizontal asymptote y=-1. And there we go. So I've crossed through my x-intercept at -3, had my little point of inflection, y-intercept, max, other point of inflection, and then other horizontal asymptote. And now I can label this. So this is the graph of y=x+3 over square root of x² + 1. So as you can see, when it's not just a rational function, there definitely is more to think about as far as the calculus side of things. Same thing would also be true if we talked about something like this, where we've got ourselves a trig function. I've been nice to us in that I've given us just an interval to look at, just from 0 to 2 pi. So that means we don't have quite as much worry to do because, of course, if there's a sine function or a cosine function or any other trig function involved, because those are periodic, we'll often have infinitely many critical numbers. So this time we're only going to be looking just inside of that interval from 0 to 2 pi. Since we're on a closed interval, it makes sense for us to figure out where we begin and where we end. So when x is 0, the y value is 0 plus 2 sine 0, which is 0. So 0, 0. And when x is 2 pi, the y value is 2 pi plus 2 times sine of 2 pi. And 2 pi is 0, so we get 2 pi plus 0, which is 2 pi. So it looks like we've got 2 points that we can plot on our graph whenever we feel like it, 2 pi, and 0, 0. This also means that we've got an x-intercept already figured out on our graph without having to do any clever work, and also the y-intercept. This is the example of a function where finding x-intercepts would be difficult because if you were looking to solve, you'd have to solve for where is 2 sine x equals to negative x. And apart from the obvious solution of x equals 0, it's not obvious what other solutions there might be for this equation. In fact, solving this equation and trying to find out where x-intercepts are, we would need to use something that we're going to see a little bit later, Newton's method. But at any rate, we found an x-intercept and we found a y value at the end of it all of 2 pi. And if we're thinking about other things that we know, the domain for sure is all real numbers. So sine is defined everywhere, so is x, which means that we're defined everywhere inside of our interval. So we shouldn't have any vertical asymptotes or any other weird discontinuities to concern ourselves with. We're also on a closed interval, so there's no need to think about or care about horizontal asymptotes. Even if this function had them for some reason, and I don't think it would, but even if it did, the fact is horizontal asymptotes happen as x approaches infinity or negative infinity, and we won't be doing that here because our x values are just between 0 and 2 pi. So that means really the only thing we need to think about is increasing and decreasing in concavity. And so let's start off with our first part and write out our first derivative. First derivative, easy enough to find. F prime is equal to derivative of x is 1 and derivative of sine is cosine. And for sure, this is never undefined. And it's never undefined because, of course, x can be anything in here, and this will be some sort of a real number, so we never have to worry about that happening. So that means we won't get any critical numbers for that reason. If we're looking for where is f prime equal to 0, we'd have to ask ourselves, where is 1 plus 2 cosine x equal to 0? And if we were to look for that, we'd be trying to find out where cosine is equal to negative a half. So if you're thinking back to your trigonometry days, just as a little aside here, of course, you might remember that cosine of pi over 3 was a half. And you might remember that there are two quadrants where cosine is negative. So there'll be two places where cosine is negative a half, one of them in quadrant 2, the other one in quadrant 3. And we are looking for solutions anywhere between 0 and 2 pi, so we will get both of those solutions as critical numbers. So if we're looking to solve where is cosine equal to negative a half, one of them is in quadrant 2, where the reference angle is pi over 3, in other words, 2 pi over 3. And the other one is in quadrant 3 with the reference angle of pi over 3, and that's 4 pi over 3. So if we're looking for these two places, so one of them is when x is 2 pi over 3, and if we wanted to find out what the y value is, of course we go back to our original function. And we'd say, well, that would be 2 pi over 3 plus 2 times sine of 2 pi over 3. And sine of 2 pi over 3 is a half. So you'll have 2 times a half, which is just 1. So basically we'll wind up with 2 pi over 3 plus 1. Which is 5 pi over 3. So one of our points for the critical number 2 pi over 3 has y coordinate 5 pi over 3. And then for the other point, when x is 4 pi over 3, the y value is f of 4 pi over 3, which is 4 pi over 3 plus 2 times sine 4 pi over 3. This time, sine of 4 pi over 3 is negative a half. 2 times negative a half is negative 1. So we get 4 pi over 3 minus 1, which is pi over 3. So we have a second point, and that's 4 pi over 3 pi over 3. Okay, so I've got my two little critical numbers, and now I want to do the little number line business to decide if we're increasing or decreasing. Of course, I have to remember that we're not just going on forever. We're looking at stopping at 2 pi, and our two critical numbers were at 2 pi over 3 and at 4 pi over 3. Conveniently enough, all of my multiples of 90 are inside these intervals. So for the first one, I could choose pi over 2. And if I look at f prime of pi over 2, that's 1 plus 2 cosine of pi over 2. Cosine of pi over 2 is 0. So our first derivative is positive 1, so we're increasing. Between 2 pi over 3 and 4 pi over 3, I would just choose pi. F prime of pi. You'd have 1 plus 2 times cosine of pi. Cosine of pi is negative 1, so you'd wind up with 1 minus 2, which is negative 1. We'd be decreasing. And between 4 pi over 3 and 2 pi, I would choose 3 pi over 2. And if I put in 3 pi over 2, I would get 1 plus 2 times cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so we get 1 plus 0, which is just 1, and we're back to increasing again. So actually what we now know is that this is a maximum at 2 pi over 3. And since we decrease followed by increasing, that it's a minimum at 4 pi over 3. So I'm going to come back and jot those down later. I'm going to fill that all in on my graph. So let's actually do that right now. I've started to put my axis down. I looked at everything was all in terms of pi over 3. So along my x-axis, I've just gone up by pi over 3 each time. So we had 0, 0, and 2 pi, 2 pi. That was the beginning and end of our graph. And then I've got my 2 points that I've just found out now, which was 2 pi over 3, 5 pi over 3. There we go. And then the other point was 4 pi over 3, pi over 3. And I know that 2 pi over 3, 5 pi over 3, that's a maximum. 4 pi over 3, pi over 3, that was a minimum. So it feels like we should probably be heading up, heading down, heading up. That's our pattern of increasing versus decreasing. For sure, we're going to have some sort of change in concavity, because where we're having a minimum, we're concave up, and where we have a maximum, we're concave down. So I'm expecting somewhere in the middle, there should be a point of inflection. So let's go and figure out where that point of inflection needs to be, and then we'll fill in the rest of our graph. So we have first derivative already done. Our first derivative was just 1 plus 2 cosine of x. So for your second derivative, derivative of 1 is 0, and derivative of 2 cosine of x is negative 2 sine x. Of course, f double prime is never undefined. And that's, of course, because it's a sine function. This is defined for any x. If we're looking for where that second derivative is equal to 0, that's where minus 2 sine x is equal to 0. And that happens to be, of course, at lots of places, at 0 and at pi and at 2 pi. 0 and pi, of course, those are the endpoints of my intervals, so I don't really need to care that much about them. I mean, potentially they're changing concavity there, but we won't see it because our graph isn't going to show what happens on either side of 0 or 2 pi. I will care about what happens at pi, because that will likely be my point of inflection. So let's just confirm that. So between 0 and pi, I'll pick pi over 2. And I find for my second derivative at pi over 2, I would have negative 2 sine pi over 2, which is negative 2 times 1. So we should be concave down. And between pi and 2 pi, I would choose 3 pi over 2. And for that, sine is negative 1, so we'd have negative 2 times negative 1, which is positive 2. So we are concave upwards. So definitely we're going to have a point of inflection when x is equal to pi. We should figure out what our y value is. And so for that, we're going to go back to our original function, which was x plus 2 sine x. Sine of pi is 0, so we wind up with pi plus 0, which is just pi. So what we've just learned is that pi is a point of inflection. Okay, so I guess now I've got everything I need to fill in the rest of the graph. I'll just plot that point pi, and then I will continue. So we are going to increase being concave down until we get to our maximum, and we will then decrease, continuing to be concave down until we get to our point of inflection, and that's at pi. After our point of inflection, we're going to still be decreasing, but we'll now be concave up until we get to our minimum, and we'll still stay concave up, but we're going to increase now until we get to our final value of 2 pi. So there we go. We've got our function f of x equals x plus 2 sine of x. Almost kind of looks like a sine graph that's sort of been pulled upwards, kind of. And that's what we've got. We've got a max, we've got a min, and a point of inflection.